Here we present the central limit theorem. If samples are of size n greater than or equal to 30, or if the x's distribute normally, then the x bars distribute normally or approximately normally, and mu sub x bar is equal to mu, as well as sigma sub x bar is equal to sigma divided by root n. Let's first get a sense of the logic of the theorem, and then we'll try to get to the meaning of the theorem. So the first thing, in order to use the central limit theorem, one of two things has to occur. Either you have to have samples of size n greater than or equal to 30, and that doesn't matter how the original data distributes. It could distribute as a bell curve, or it could distribute chaotically. It doesn't matter. If your sample sizes are of n greater than or equal to 30, you can use the central limit theorem. The other condition for which you can use the central limit theorem is if the x's distribute normally. So if the raw data distributes normally, then it doesn't even matter. You could have a sample size 10. That's okay, as long as the original x's distribute normally. So either one of these must apply, or both is fine as well. Then, if one of these two things applies, the conclusions of the central limit theorem are that the x bars will distribute normally, and mu sub x bar is mu, and sigma sub x bar is sigma by root n. That's the logic of the theorem. Let's now see if we can get some understanding of what exactly it is saying. This visual representation here can be really helpful in understanding the central limit theorem. At the top here are your conditions. They're the conditions that need to apply, either one of them, number 1 or number 2, they need to apply to then be able to make the following conclusions. Notice first that the conditions, either this one or this one, are about the raw data value, the x's. And then if either one of these two is satisfied, then your conclusions about the central limit theorem are about the x bars and how they distribute. So, condition 1, you can have any population distribution. It could be this chaotic looking thing here. As long as n is greater than or equal to 30, your sample size is 30 or more, then it doesn't matter. This is clearly not a bell curve. It doesn't matter what that distribution looks like. As long as n is greater than or equal to 30, then the x bars will distribute approximately normally. That's where the word approximately came from in the theorem. If the original data already distributes normally along the bell curve, then even if you have small sample sizes, something less than 30, or something more than 30, or 30 itself, it doesn't matter. Any sample size, if your original data is distributed normally, then the central limit theorem guarantees that the x bars will distribute normally. And in both of these scenarios, this one and this one, the x bars distributes normally, and mu sub x bar is precisely mu, and we saw sigma sub x bar is precisely sigma divided by root n. This is the central limit theorem. Let's now see if we can apply it. Here is our first example. IQ distributes normally in the adult population. We've seen this before. The Wechsler adult IQ test has mu equals 100 and population standard deviation 15. Suppose 9 adults are chosen at random. What's the likelihood their average IQ is above 105? This is a typical central limit theorem problem. And the reason the central limit theorem applies here, and we often use CLT to represent the central limit theorem, is because while we have a small sample size of only 9, we know that the original data values, the x's, they already distribute normally. So while we have a small sample size, since we know that the data distributes normally, then it doesn't matter what the sample size is. We know that the x bars will distribute normally, and that precisely mu sub x bar is equal to mu, and sigma sub x bar is equal to sigma by root n. And the reason we're interested in the x bars is because this is a question about what's the likelihood the average IQ of those 9 adults is above 105. So what's the likelihood that x bar is above 105 for those 9 adults? Now the computation goes essentially the same as it did in previous sections. However, we just have the adjusted variables. Specifically, mu sub x bar is mu, and sigma sub x bar is sigma divided by root n. But also, we need to reconfigure our z-score computation. Before it was z equals x minus mu over sigma. That's to get a z-score from raw data values x. Now we want to get a z-score from the distribution of x bars. So now z is equal to x bar minus mu sub x bar divided by sigma sub x bar. So you notice it has the same structure as it originally did here. So we're going to go through the computation in much the same way that we did before. So we want to know what's the probability, and now I'm going to specifically use the notation because I don't want to know if one person has, what's the likelihood one person has an IQ above 105. I want to know what's the likelihood that 9 of them have an average IQ, x bar, greater than 105. So this is my question. What's the likelihood that the average IQ of the 9 people is greater than 105? Well, just like before, we now have our strategy of going from x bar to z, and then z to the corresponding probability that we want. So right now, we have an inequality with respect to x bar. We need to get that with respect to z. So x bar greater than 105 is the same thing as z is greater than. Using this formula, we'll plug this stuff in. We've got z equals x bar is 105 minus mu sub x bar, which is the same thing as mu, that's 100, over sigma sub x bar. Sigma sub x bar is not the same thing as sigma. So let's go over on the side here really quickly. Sigma sub x bar is equal to sigma, which is 15, divided by the square root of the sample size. So it's the square root of 9 that we're dividing by, and we get 15 over 3, which is equal to 5. So sigma sub x bar is 5. Sigma was 15, but we don't want 15 here. We need the newly scaled sigma sub x bar, which is 5. Completing this arithmetic, we get 5 over 5, which of course is just 1. The question of what's the likelihood that x bar is greater than 105 is the same thing as what's the likelihood that z is greater than 1. Now, once we've converted from x bars to z's, we can now use the standard normal distribution table to find out what this probability is. According to the standard normal distribution table, the likelihood of z being less than 1 is 0.8413. But of course, we don't want the likelihood that it's to the left or less than 1. We want the likelihood that it's to the right or greater than 1. So to get the area to the right, we do 1 minus the area to the left. And this leaves us with 0.1587. So there is a 15.87% chance that if you choose 9 adults at random, that their average IQ is above 105. So now let's compare this problem to a problem from the previous section where we didn't use the central limit theorem. The previous problem was IQ distributes normally in the adult population. The Wechsler adult IQ test has mu equal 100, sigma equals 15. Suppose an adult is chosen at random. What's the likelihood his or her IQ is above 105? Whereas our new question is IQ distributes normally in the adult population. The Wechsler adult IQ test has mu equals 100 and sigma equals 15. Suppose 9 adults are chosen at random. What's the likelihood that their average IQ is above 105? So the big difference here is you're choosing one adult in the original problems, and now in these new problems, you're choosing a group of adults. And here you wanted to know what's the likelihood that person's raw data value is above 105, whereas here we want to know what's the likelihood their average, the x bar, is above 105. So from a previous screencast, we got an answer of 37.17% to this one and 15.87% to this one. Why did that happen? What's the difference? Well, let's think about, again, the distribution of the x bars compared to the x's. So in blue here, let's draw up the x's. We know that it distributes normally. It looks something like that. Now, how do the x bars distribute compared to those x's? So again, in blue are these x's. Let's switch to red for the x bars. Well, we do know that the x bars also have the same mean. Mu and mu sub x bar are the same, so they should both be centered about this vertical red dotted line, which corresponds to the value 100. But we do know with the x bars that sigma sub x bar is smaller than sigma, meaning this is going to be compressed in comparison. So the red one, the x bars, is going to look something like this. And if 105 is roughly about here, notice the difference. To the right of 105 under the red curve is smaller than to the right of 105 under the blue curve. Hence the reason we got 15.87% when we used the central limit theorem as opposed to 37.17% when we did not use the central limit theorem. Essentially, with the central limit theorem or with groups of people, it's harder to get away from the mean than it is to get away from the mean for one individual person.